My goal was simple. It was to answer the following questions on artificial intelligence systems. First, when are two AI systems identical as AI systems? And then, when does an AI system persist, namely exist at different times, despite it changing, affecting it? My approach was to answer these questions by providing formal rules called identity criteria that make use of the trustworthiness of AI systems as principle to talk about their identity and change over time. The significance of my approach is twofold. First, it shows that the metaphysical identity of AI systems is intertwined with the norms and practices of the social systems in which these artifacts are designed and deployed through their trustworthiness. Second, my approach suggests that if we can formally control the identity of AI systems, then we can regulate their evolution, minimizing societal risk stemming from the poorly understood change over time, while providing a solid foundation for philosophical, scientific, ethical, legal, and regulatory reasonings on AI. And now, let us describe the methods I used in my paper in some detail. First of all, what are identity criteria? Well, these are formal rules that typically use equivalence relations to determine whether entities are the same. They are introduced for sortal entity, namely concepts of a distinct sort of kind. Think about the kind of all rocks, of all seashells, of all humans, planets, and so on and so forth. These formal rules typically admit two forms: synchronic identity criteria that formalize identity at any point in time, and diachronic identity criteria that formalize identity over time. For millennia, the orthodox view suggested that man-made objects, artifacts, do not admit identity criteria. Think about the famous ship of Theseus puzzle. The problem here lies in the loose relation between the function, that is the purpose of the artifact, and their material makeup. However, Carrara and Fermat challenged this view by stating that the appropriate conjunction of the function, operational principle, and normal configuration of artifacts allows us introducing the identity criteria for these man-made objects. Here, the operational principle expresses the rules that specify the correct functioning of the artifact, which are then integrated in the normal configuration. My idea was to endorse Carrara and Fermat's view, applying it to AI systems as follows. First, using their technofunction to define the AI system kinds, and then introduce trustworthiness as the operational principle of these systems. As a result, I was able to introduce identity criteria for AI systems, but before showing them, let us justify trustworthiness as the operational principle of AI systems. Following a principled approach, we define AI trustworthiness as the collection of capabilities that are expression of the normative and practical demands of a social system. Examples are fairness, transparency, and reliability, among others. These principles are then translated in system requirements called trustworthiness contracts. These contracts specify what functionalities the system is expected to satisfy to function correctly. Then, the collection of these contracts can be called the trustworthiness profile of the AI system designed in a given social system. Our assumption here is that trustworthiness is a quantitative capability of an AI system that varies over time, typically decreasing due to phenomena such as distributional change, among others. Therefore, retraining machine learning models in AI systems can be seen as an intervention to increase the trustworthiness levels of these systems over time. Finally, our identity criteria. Synchronic identity. At any time t, two systems are identical if and only if they perform the same function and meet the same trustworthiness standards at equal levels. Diachronic identity, at different times, a system persists, namely exists at those different times, if and only if it upholds its commitments consistently in the same kind. Please note that these identity conditions are quite liberal. They allow for retraining and redesign of systems without impacting their identity, so long as the trustworthiness profiles and levels are preserved. In the manuscript, there are quite a few examples of identity scenarios for AI systems. I leave them to you in case of your interest. Here I briefly introduce two. Imagine two hospitals using two copies of the same medical AI system. Over time, one hospital, Hospital 1, retrains the system, the other, Hospital 2, does not. Are the systems identical over time as medical AI? In general, they can be identical despite retraining, but they are not identical if their trustworthiness levels diverge or changing affecting the trustworthiness contracts of these systems are implemented. Ethical consequences for patients and clinicians have to be discussed. The second example, suppose a company is selling an LLM-based app in a given social system. The CEO of the company wants the app to be deployed in another social system with stricter social technical norms. If the app redesign introduces new trustworthiness contracts, then are the apps the same app? Our framework says no. They are numerically different systems in the same AI system kind, although they perform the same function and may share design similarities. Regulatory and legal aspects of this phenomenon need to be discussed. Conclusions. AI systems like people, organizations, they do change, but not all changes are identity breaking. By grounding identity in trustworthiness, we align metaphysics with real-world governance concerns. Our hope is that this theory provides a principled basis for reasoning about the identity of AI systems over time. I thank you very much.
Let's thank Andrea.